Bismillahirrahmanirrahim. Assalamu alaikum. So here are the course contents of digital signal processing. Broadly classifying, we can divide our course into three major portions. First one is basics of signals and system. In this part we will discuss some introduction about digital signal processing. What's the major difference between discrete and continuous signal? What's the difference between analog and digital? We will discuss some advantages of DSP and we will discuss some applications of digital signal processing. Then we will discuss concept of frequency in continuous time sinusoids, and the same will be discussed for discrete time sinusoids. After this we will look at some elementary signals and its types, and then we will discuss manipulation of signals such as time shifting, time scaling, time folding, and then we will come to the system part and we will discuss some basic system configuration and its classification, as well as some system properties such as stability of the system, how we can determine stability of the system, how we determine the linearity of a system, what is time variant system, what is time invariant system, what is causality. So some system properties will be discussed in that area. After that we will look into the mathematical tool which is known as convolution sum. So as we are discussing a discrete time signal, so we will look at discrete time convolution sum. Then afterwards we will discuss discrete time correlation, which is somehow similar to the discrete time convolution. We will see what's the major difference between the two techniques, what are their mathematical expression, and what are their applications. Afterwards we will discuss the conversion of an analog signal into digital form, how we can achieve the conversion, is there any criteria, and how we can convert an analog signal into digital one accurately, what problems arises during this conversion, and how we can overcome it. So these all things will be discussed in the first part, which is basics of signals and systems. Now coming to the second major portion, which is frequency analysis of signals. In this portion we will discuss some of the mathematical methods, mathematical techniques and tools we utilize for frequency analysis of any signal, which means that which frequency components or which frequency contents are present in that signal. So in this part we will discuss majorly about the Fourier tool, which is commonly used to analyze the frequency components present in any complex signal or any real world signal. In this portion we will discuss techniques such as continuous time Fourier series, or we can say CTFS. Afterwards, continuous time Fourier transform or CTFT. Afterwards, discrete time Fourier series, also known as DTFS, and discrete time Fourier transform, also known as DTFT. And afterwards we will discuss discrete Fourier transform and one of the very robust technique, which is fast Fourier transform or FFT in general. So we will discuss the methodology of all these techniques. We will learn bit about their computational algorithm and the significance of each technique. Coming to the third major portion, which is designing of discrete time systems. In this portion we will first discuss general representation of discrete time systems. What are the methods? What are some common methods to represent discrete time systems? Either mathematical model, either by block diagram, and so on. And afterwards we will discuss what are the various mathematical tools to analyze any system. In the previous portion we are analyzing signals, and in this portion we will talk about systems. So in this portion we will analyze the stability of the system, we will comment about the linearity of the system, and we will talk about overall about the systems. So afterwards we will see the relationship between some famous mathematical tools such as Fourier, which is also discussed in the previous portion, then Laplace, and as well as Z transform. We will see that among these tools which tool is better, or we can say in which conditions we can apply which tool. Afterwards we will learn how we can take the Z transform of the signal, or how we can determine the Z transform of any signal, what's its significance. Then we will discuss about the relationship between difference equation and impulse response, and the transfer function of any system. Finally, we will look at the basic design aspects of discrete time system, how we can design any discrete time systems, what are the major classifications such as finite impulse response system and infinite impulse response system. We will design these type of systems in this portion. So I hope after listening the course content you are much curious to learn about these tools and techniques, and inshallah you will enjoy and have a healthy learning session of digital signal processing. Before proceeding, please note the course material for this course. First of all, textbook. We will follow digital signal processing principles, algorithm, and applications by John Prokes. You may refer to any edition which is third or above. We will follow this book as a textbook for our course. As far as reference books are concerned, you may refer Discrete Time Signal Processing, by Alan Oppenheim, third edition or above, or you may refer to Understanding Digital Signal Processing by Richard Lyons, third edition or above. And apart from the textbook and reference book, you may refer to my lecture slides. So starting Introduction to Digital Signal Processing. In the upcoming slides, we will see the major difference between continuous time signal and discrete time signal. Afterwards, we will discuss the major difference between an analog signal and digital signal. After discussing these two major differences, we will comment how the discrete signal is different from the digital signal, as these two terms are not the same. Discrete time signal is different thing and digital signal is another thing. After discussing these differences, we will comment the applications and advantages of digital signal processing, and we will discuss some basic block diagrams of digital signal processing. A question may arise in your mind that what is signal? So a signal is any physical quantity that varies with one or more than one independent variable. This independent variable may be time in many cases and may be another independent variable. As you can see in this equation that x of t is equal to 2t, that is, we have an expression representing a signal, and this equation is in the linear form. Another example, in this equation you can see that we have 5t square, which means that the equation varies quadratically. In the first equation we can see the equation varies linearly because we have 2t, and in the second equation we can see we have t square, so this equation varies quadratically with the time. We may have another equation such as z of t is equal to 5t cube. So in this expression we can say that t varies cubically with this signal. Apart from this equation, we may have any equation that depends upon more than one independent variable, such as a depends on x as well as a depends on y, and we have an expression 5x plus 6xy showing that a depends on both the variables x and y. So these are some basic equations in very generic form and in the very simplest form to understand the concept of signals. But in the real world we may encounter any signal which is very complicated, so you can imagine that the mathematical expression of that signal must or should be very complicated and in maybe in complex form. Just for example, we have taken an image or plot of an ECG signal. By looking at this graph, you can comment that the mathematical expression of this ECG signal is very much complicated. Although it depends upon a single independent variable, that is time, but again the expression should be very complicated, as you can see from the graph. Another real world example may be a speech signal, so you can see that how complicated this signal is. So you can again comment that the mathematical expression of this signal is very much complicated. System. You may define system as a combination of different circuit elements arranged in a particular manner to perform a specific operation or a specific task. So a system is any physical device that performs operation on the input signal. Here you can see that we have a circuit arranged in a specific pattern to perform a specific task. What is going on in this circuit? Here we can see that we have one capacitor connected with a resistor in a particular manner. So this R and C arranged in a particular manner forms a system, and to this system we have an input, that is Vin, voltage as an input. We apply voltage to this circuit and correspondingly we will get V out or output voltage from these two terminals. So this specific arrangement of circuit elements performs some specific task, and what this circuit is performing right now, this is basically a high pass circuit. What is high pass circuit? High pass circuit is in easier term is the circuit which allows higher frequencies to pass through and attenuates the lower frequencies. As you can see in this figure, we have frequency on the x-axis and gain on the y-axis. So in this graph you can see that when we have the frequencies which are lower in magnitude, then these circuits provide zero or very lesser gain to these frequencies. And when our frequencies are above the FC value is a certain value known as cutoff frequency, and it depends upon the circuit arrangement value of R and C that decides what is the cutoff frequency for our circuit is. So you can see that in this graph, when the value exceeds the cutoff frequency, our circuit provides a higher gain to these frequencies which are of higher magnitude. So in simpler terms, lower frequencies are attenuated and the higher frequencies are passed through this circuit. After getting the concept of signals and systems, we may interlink these two terms with the help of block diagram. Here we have a block showing a system or representing a system. At this stage, we are not interested in the specific function or behavior of this system or the properties of this system. This system may be a stable system, or you may say this system may be an unstable system, or you can say that this system is a linear system, or this system may be a non-linear system, like this system may be a time variant system. So we are not interested in all these properties at this stage. We are only considering this system as a generic block or a generic system which is used or designed in a specific manner to perform a special or certain task. So to this system we have an input signal. This input signal is also termed as excitation to this system, because when we apply this input to the system, this signal basically excites the system and system will respond accordingly and we will get the output signal. So we can term input signal as an excitation and the output signal as a response. A question may arise in your mind that what is signal processing. So the signal processing is the manipulation of input signal to get the desired shape at the system output, or we can say the manipulation of input signal to get the desired output. Or in other words, we can say signal processing as the mathematical operations performed by the system on input signal to get the desired output. So what's the main reason of doing signal processing, or what's its main objective? So the main objective of doing signal processing is to extract the meaningful information or the useful information carried out by that input signal. And the method of extracting this useful information from the input signal completely depend upon the type of input signal, which means that this input signal may be in continuous time domain, or maybe in discrete time domain, or digital form, or analog form, or maybe of any other classification. So the method of information extraction depends upon the type of the signal, and secondly the nature of information being carried by that input signal. And by the term nature of information, we means that how complicated the signal is. So if the signal is more complicated, we have to apply more sophisticated and robust signal processing techniques to extract the useful information and to get the desired output. So we understand the term signal processing. Now, signal processing can be broadly classified into two major classifications. First one is analog signal processing, and the second one is digital signal processing. We will see the difference between these two classifications, that is analog signal processing and digital signal processing, in the later slide. We will learn analog signal processing with the help of block diagram in this slide. Suppose we have any real world signal, and it is not necessary that this signal is in the form of electrical parameters such as current or voltage. So we have initially a signal which is a non-electrical signal. So before processing this non-electrical signal with the help of electrical circuitry, we may first convert this signal into electrical compatible form with the help of transducer. What this transducer will do? It will convert a non-electrical signal, which may be any physical, you may say it is a physical phenomena. So physical phenomena in a non-electrical signal form, and with the help of transducer you are converting this physical phenomena into current or voltage waveform, which is varying with time. So you will get an output signal, and this output signal is now in the electrical form, maybe a current waveform or voltage waveform, and this output signal is analog in nature because mostly real world phenomena or physical phenomena are analog in nature. Now this input signal is applied to an analog signal processor, which is a system, and this analog signal processor will convert this analog input signal into an analog output signal. That is, this ASP block processes this input signal and extract the meaningful information or the desired information on this input signal, and we will get an analog output signal. Now understanding digital signal processing with the help of its block diagram. Again, we suppose that there is some non-electrical signal, and we first convert this non-electrical signal into an electrical compatible form with the help of transducer, just in the case as in the case of analog signal processing, and we will get an analog output which is the input signal to a special block which is called analog to digital converter. So this is the major block or the most important block which converts the analog signal into digital form. Without the help of this block, we can't do digital signal processing as this signal is in analog form. So we will first convert this analog signal into digital form with the help of this ADC block, and the output of this ADC block is digital signal. So we have a digital signal which is input to another block which is a DSP block or a digital signal processor block. Just as in the case of analog signal processing, we have an analog input signal and an ASP block, because there we want to process an analog signal, so we have ASP block, but here we have a digital signal as an input signal, so we have a digital signal processor block. Another specialized block with this digital signal processor or linked with this DSP block is the memory block, because this block holds all the operation, or you may say all the computational steps or all the procedure which is done by this DSP block on this input signal. All this algorithm is stored in this memory block. So this memory block is linked with this DSP block to hold the algorithm which needs to be performed on the input signal to get the desired output signal, and this output signal is again in the digital form. After this, we may have an additional block which is a DAC block, DAC or digital to analog converter. You may see first we convert the analog signal into the digital form, and after processing with the help of this DSP block, we have a digital output signal, and this digital output signal may be converted again into the analog form with the help of DAC block, but this block is an optional. If you don't want to convert your signal into analog form, you may get your output here. And now what's the output of this DAC block? As this DAC block converts the digital signal into analog form, so we have an analog output signal. Summarizing this block diagram, we have non-electrical signal which is converted into electrical compatible form with the help of this transducer, and transducer, we have an output of the transducer as an analog signal, and this analog signal is passed through the analog to digital converter block, and this block converts analog signal into digital form, and this digital signal is applied to the input of a digital signal processor, and this DSP block is linked with the memory block, and this memory block holds all the algorithm which needs to be performed on this input signal. And we have an output with the DSP block, and this output signal is in the digital form, and we can convert this digital output signal into analog form with the help of DAC block, or digital to analog converter. So we have two types of signals, or two nature of signals encountered in this block diagram. First one is CTCV signal, and the second one is DTDV signal. CTCV signals are the analog signals, and DTDV signals are the digital signals. Here we have CTCV signals, that is, it is of analog form converted into digital form, and in the last it will again converted into analog form, and we have analog form of output. In this slide we will see the major difference between continuous time signal and discrete time signal. So here are the two plots. First one is for analog signal, which is a continuous time signal, and the second one is for a discrete time signal. In the first plot you can see that if we consider x-axis as a time axis and y-axis as an amplitude axis for both these plots, so in the first plot, which is for analog signal, our function exists for each and every possible value of time. That is, function exists for time t is equal to -2 second, function also exists for time t is equal to 0 second, function also exists for time t is equal to 2 seconds, 4 seconds, and so on. And the function is not only limited to these values, but the function also exists between these values. That is, function also exists for 0 to 1, and in between 0 to 1 we have infinite values like 0.1, 0.2, 0.3, and between 0.1 and 0.2 there are again infinite values like 0.001, 0.002, 0.003, and again 0.001 and 0.002 also contains infinite values like 0.0001, 0.0002, and for all these values this function exists, so we get a continuous plot for each and every value of time. Or in other words, we can say we have a function magnitude, or we have a function value for each and every value of time. So this graph is continuous, or this signal is continuous in time. So summarizing the concepts, that continuous time signal or analog signal is defined for each and every value of time, and they can take any value on a continuous time interval. So this is analog signal, which is continuous time signal. Now come to the discrete time signal. As you can see that discrete time signals are defined only at certain specific values of time. You can see in the graph we have a limited values of time for which your function is defined, or for which your function exists. Or if one say ask you to tell him or her the value of function at 0.01 or 0.02 or 0.001 or 0.002, you may not be able to answer him the exact value, because you have the information for only specific intervals or specific points in the graph. In this figure, the intervals are also equi-spaced, but we can also take different distances between the two interval, so we are not bound to take the equidistance intervals. But why we are taking, or why we generally opt to take equidistance intervals? This is because we just want to simplify our calculation, and for our easiness we take equidistance intervals for a discrete time signal. In this slide we will discuss the major difference between an analog signal and digital signal. Analog signal is same as we seen in the previous slide, which is a continuous time signal, and if we convert the signal into discrete time signal, we have to take certain specific values of time and plot the function. Just you can see in the figure, the time axis is discretized and your function exists for specific values of time. So this is discrete time signal. Now if you look at the y-axis of this signal, so the y-axis is again continuous. That is, this function can take any value of the amplitude. But if we limit this signal to take on values from a finite set of possible values, then this signal is said to be a discrete valued signal or a digital signal, like this. You can see we restricted this signal to take on value from this possible finite values as shown from the dotted lines, and this signal adjusted its amplitude accordingly and we will get a digital signal. So generally speaking, initially we have an analog signal. From that analog signal we obtain discrete time signal by sampling the time axis, which is the x-axis, and if we sample the y-axis also, we will get a digital signal. Usually this possible set of values are also equidistant, so they can be expressed as an integer multiple of the distance between the two successive dotted lines.